Hi, welcome back to Moose and Chemistry. This is about Gibbs free energy. And what we're going to do today, we're just going to define the basic terms of Gibbs free energy, and then we're going to give you the equation of Gibbs free energy. Well, Gibbs free energy is a state function that relates to enthalpy and entropy. So what is entropy? Entropy is this guy right here, all right? Energy that is distributed or dispersed among various motions of the molecules of a system. In other words, what is its state of disorder? It's denoted by delta S, and it is done in kilojoules per Kelvin. Now, enthalpy, on the other hand, is heat that is evolved, which means that it is lost or absorbed in the reaction. It's denoted by delta H, and it's measured in kilojoules, okay? Kilojoules. So we'll make our little J there for you a little bit better. All right. Now, a spontaneous process, however, is a process that can proceed in a given direction without the need of outside energy. So when we look at this, what we're going to do next is we're going to write the equation. All right, now we're going to be looking at this equation from Gibbs free energy. So Gibbs free energy basically is delta G equals delta H minus T delta S. Okay, let's look at parts of this equation. So delta G is the free energy. That's our free energy. And that will be denoted again in kilojoules. Our delta H is our enthalpy. Okay, so that's our enthalpy. And remember what we said about enthalpy. Enthalpy is the heat that is evolved or absorbed in the reaction. So that's going to be also measured in kilojoules. T is our temperature component. All right, and our temperature is going to be measured in Kelvin. And then delta S is our entropy. And remember that our entropy is in kilojoules per Kelvin. Okay, now also remember that entropy is the energy that is distributed or dispersed among the various motions of the molecules of a system. In other words, we're talking about the state of disorder. Now, there's a little thing. If delta G equals a positive number, then this is called non-spontaneous. If delta G is negative, then the reaction is spontaneous. Okay? That's really, really important to remember. All right, so we're going to pause this video here for a second, and we're going to look at a little bit more. Okay, let's look at this problem. Let's make a problem up. Let's say our delta H has a value of negative 232 kilojoules of energy. And let's say our delta S has a value of 138 joules or kilojoules of energy. All right, yeah, and that's going to be our KS, kilojoules there. That's right. And then let's say our T is going to be 273 Kelvin. Well, given this energy, is this equation going to be spontaneous, or is the reaction itself going to be spontaneous? So let's figure it out. So delta G equals negative 232 kilojoules minus the temperature, which is 273 K, times our enthalpy, which is 100 and 38 kilojoules over K. All right, now let's see here. Our K's will cancel out. So when we do the math, we get delta G equals negative 232 kilojoules minus 37.67 kilojoules. And our delta G is going to equal negative 194.3 kilojoules. Oh, so you know one thing we should do, if we're going to change this, we should have said that this was point 138 kilojoules, because we're going to take that and make that into kilojoules, not joules. Okay, so we're going to do that, and we get the math. This is what we get. All right, and so since this is negative, this happens to be spontaneous. So this is spontaneous. Okay. Okay, guys, I just noticed one thing about my calculations. I meant to put a negative sign with this right here. So that would make this a negative sign here. And this would be a negative of a negative. And when you change that, this becomes positive. And that's how we get the negative 194.3 kilojoules. Sorry about that. All right, now there is a table that we can set up that would give us whether, delta G is going to be spontaneous. So I'm going to go ahead and clear the board here for a moment, and I'm going to give you that table. Okay, so how do we know when delta G is going to be spontaneous or non-spontaneous? So remember that delta G is Gibbs free energy, and it's a state of function that relates between enthalpy and entropy. So what we're going to do is we're kind of like a Punnett square and they do in biology. I know, biology. Grr. Anyway, so we're going to go set this up. All right, that's delta H negative and delta H positive. This is going to be positive delta S and negative delta S. Okay, so when entropy is positive and enthalpy is negative, the numbers are always spontaneous. Okay? And when entropy is negative and enthalpy is negative, it's spontaneous at high temperature. Oh, high temperature is non-spontaneous. Correction. High temp, non-spontaneous. And at low temp, it's going to be spontaneous. Okay, and when delta S is positive and delta H is also positive, high temp, it's spontaneous, and low temp, it's non-spontaneous. Okay, and then what if delta S is negative and delta H is positive? Then it's never spontaneous. Okay, never. So, is there another equation that we can use? All right, there's one other possibility. For example, if delta H and delta S are known, there's another version of the Gibbs equation that you can use. it would be delta G, and this would be reactions, equals delta G naught products minus delta G reactants. That's if you know delta H and delta S. All right. Well, listen, guys. You be snarly, you be awesome, and we'll see you back here at Moose in Chemistry.